Uh, Good morning, everyone. As the presenter said, this is the first time I'm here, so I'm pleased, pleased to be there with you, and I'm also not, because I feel the responsibility, the pressure. So I hope you will enjoy this talk. So let's start with. Thank you, thank you very much. Let's start with by making some introductions. I am ROCCO PEZZANI, and I work for Würth Phoenix SRL. What is Würth Phoenix? Würth Phoenix is an Italian company from the Würth Group that provides IT services and products for other companies of the Würth Group and other companies as well. And about me, I'm a consultant and a senior system integrator, meaning my work is going from customer to customer and make disasters by installing NetEye. What is NetEye? NetEye is a software built by Würth Phoenix, is our unified monitoring solution that is based on Icinga soup, and it brings together several other software that I think you should already know. We have Elasticstack, the full Elasticstack, InfluxDB, Grafana, GLPI, and TopNG. Everyone you can dream to have in a unified monitoring and CM solution. We also have, we also provide it as a service, as a cloud service, and it is named NetEye Cloud for the ones who are interested. But today I'm not here to talk about nor NetEye nor Würth Phoenix. I'm here with Thomas to talk about SNMP-based monitoring and trying to bring a breath of fresh air in this old world. So I said SNMP-based monitoring, what it is. I trust you tried at least once to monitor one device using SNMP, and I'm not talking about routers, switches. Those are pretty easy, pretty standard. I'm talking about something that is different, a bit more complex, like UPS, racks, air conditioner, environmental sensor. Why not also coffee machine, if you have one. And the experience is, everything is based on shared standards, so it is amazing. It's easy, amazing, and how we can say it? Data are stored in a standard way, are easy to access, and they are the same across each vendor. So the MIB database is very lightweight. It has it is described by a few MIB files that are well tested, well documented. You can find them everywhere, so a pretty easy word. And the last thing, monitoring plugins. We have some of them, and they are well tested, maintained, and performs very well. So no, I don't think it is the SNMP-based monitoring world. So let's face the truth. Everyone with a bit of experience knows the biggest problem. Each vendor does what he pleases with his devices, and also devices from the same vendor provide the same data with subtle differences that make you trash your work after some time. So as a consequence, proprietary branches in the MIB database will grow like crazy, resulting in a lot of MIB files that you have to find, download. And you don't know if dependencies are well documented, so you don't know if you have everything that you need to perform the monitoring. As a result, obviously, the MIB files are not tested. They contain a lot of semantic error, so this is a very difficult word to work with them. And last thing, monitoring plugin. Because everything is not standard, you have a monitoring plugin for each feature of each model of each vendor. They are not optimized. They require a lot of computational power from both Icinga side and the network device side, and they are not maintained. After some month, you can find them rusting and dusting in some GitHub branch. So it's a sorry land for brave people that usually become lonely people after some month. I don't think you know, but Thomas GELF and Würth Phoenix share a deep and long history of friendship and work. So deep that sometimes we find ourselves around the table dining together. No? Not so much?
Shortly.
No? Okay.
We do, we really do.
Okay. Yeah, I know. So, long story short, let's imagine a table where people from Würth Phoenix and also Thomas GELF are sitting. Someone's starting a bit of discussion about a MIB browser. We need it in NetEye or not? We have to build it, use a third-party one. A difficult discussion, so we need a bit helper for everyone. And then after this, Thomas GELF did the magic. He brought up a laptop over the table, showing us a bit of an unfinished Icinga Web 2 module. After some seconds of confusion, we found out that the potential of this module and It was what we were looking for. But he said also, hold your horses, I have some idea in mind. And after we heard those ideas, we are sure that this module can become a killing feature for SNMP-based monitoring for all of you, basically. So we, Würth Phoenix, Thomas GELF, gathered out our forces to start this long journey, requested the help of some of our most trusted company, and started to build this module.
Thank you, Rocco. Good morning. So, talking about beers, that's the right moment to hand the mic over to the Germans. Germany is technically not so correct. I have been born in the Italian Alps, South Tyrol, if you ever heard about it. Nice region in northern Italy. That's where originally I'm from, but since more than 10 years I live here close to Nuremberg and work at NETWAYS, the nice company running this event today. And yeah, usually I work as a kind of consultant and work the whole years with our customers on their specific monitoring projects. And usually, well, I'm not that slow, so there remains a little bit of time to work on some fun pet projects like the Icinga Director, Icinga V3DB, and I kickstarted a lot of our modules and so on. So this is what I do, and I've been sitting there and with Würth Phoenix, and they told me, well, we want to have a MIP browser, and I was, as Rocco told you, I wasn't really excited because yes, I had something like this, but I had many more ideas what you could do with SNMP in a monitoring world, and I was really happy to finally have someone allowing me to do it, just they wanted to have the MIP browser first. And this didn't fit my plans. Because my idea was, well, first we write something that works solid and well with SNMP, and then we can add the browser. Because UI things come later on. But I haven't been able to convince them, and you know, it's the customer. So the deal was first the MIP browser, and then you can do other fancy stuff. So what did we do? We wrote a MIP browser. This is a screenshot from its Git repository, but it's also a real-world screenshot from the installation we're running here right now. And well, it just works. It's a web application where you pick some MIP files, like 1,000 of them, drag and drop them to the browser. And as long as you configure the web server accordingly and allow an upload of that size, it processes all the files and stores them in a kind of database, optimized for OIDs and MIPs, of course. And yeah, that's currently, these numbers are real. So I have a 5-figure number of MIP files in the database, and most of them are successfully have been parsed. I'm a little bit unhappy about this number. Behind this, just to parse the MIP files themselves, I'm using a very old Perl library, just very low somewhere hidden, and wrote a little wrapper that gives me some a JSON file with the data in it, and then I'm doing more voodoo with the data. It works really good. I'm a little bit unhappy with those 1,500 files that are failing. It's, per definition, it's their fault. So we'll see on one of the next screenshots that this module is going to show you why it is failing. It's pointing you to the error, and you can fix this, and then it goes on. But still, I understand the errors. By definition, they're wrong. But you know, it should work out of the box. So in parallel, I started writing on a completely new MIP browser I wrote by myself. And there it's, this number is going to go way higher. Because I wrote it in a more tolerant way, and I have full control over what I permit and what I don't. And just this is, for now, this is how it works. This is on GitHub, and with low priority, we are also bringing on this new parser. So that's what you're seeing right now. It was what we have right now, but it's going to be way better. So what are we showing in the web module? We see MIP header information, so you click a MIP file and you see the process MIP file, you see who wrote it, you see all the dependencies. That's pretty cute, because if one of the dependencies is missing, it shows you the missing dependencies. You can already have a look at the MIP file, but really use it, you have to ship the other dependencies, and as soon as you have all of them, you can click them here, it is ready and you can work with the file. Then, well, there are different views like filter by organization and so on, and there are a lot of them. Of course, we have a tree view, so if you click a MIP file, you go directly there. You can search them for the text name, for the OID, of course, and if you want to show it its details, it gives you more insight. There are also types, and not in this MIPS, but there's also a tab with trap details. So if a MIP has traps, it shows them, it knows about them. And here, for example, we see a MIP for a configuration for a printer with multiple items in that data type that has been defined in that MIP. This is how it looks like to upload the MIPS. Just, drag and drop. Really, a lot of them, it works fine. And there are also CLI commands where you can say, okay, process this directory and go on. If a MIP file fails, it looks like this. So it says, well, I have a problem here on this line. Here it is the trailing comma, where it is not satisfied, but in my beliefs, that's an error. It is an error, technically, but yeah, we could accept it. So this is something the new parser accepts. Currently, files like this you would be forced to fix files like this. It shows you where the error is, so it should be pretty easy to spot. But yeah, that's where we are right now. So it works. It is on GitHub. Currently, my personal namespace is going somewhere else later on. And the roadmap for this one is I want to replace the MIP parser we have right now. And what I didn't show, I don't even know if I have a screenshot. Yeah, I have one. There's a nice hook in there. So if you click an OID somewhere, it's if another module, we're talking about this right now, or we'll talk about this right now, it will present you, it's a drop down, it will be a not a completion field later on that shows you a lot of devices you have in some other module. And you can use this to walk live on the device remotely. So you can have portals in different zones and say, well, I have a problem with that OID. Let's have a look on the device on that node in, I don't know, Milan, and I have a satellite there, and I walk that one. Yeah, but this was just MIP parser for me. It was the client wanted to have it, so I had to obey, and we finished this module, it works, and then we went on to the funny stuff, and that's why we're here today. So next part have been a lot of components. So we wrote a module that's currently it's called inventory. So we have a device inventory, not only for SNMP, but in a module agnostic way, where a lot of modules could ship or store some data. Currently, it has, well, we'll see it right now. We have this nice MIP browser, which initially I hated it, but right now I really love it. I love it. I use it every day, but it helped me a lot to write the rest, what we're going to see right now. Just for fun, I integrated draw.io and so on. So I don't even know if we showcase it today, but this will also be nice. And then the most important part for me was distributed kind of edge computing monitoring. We implemented, I don't know if, who is using vSphere DB, the module? Okay, cool. One feature request we have there is to run it remotely on a satellite. This is currently not possible. And we started to write a framework to run modules like this in different zones, in different firewall zones, and so on, and distributors. Irideos is here today, a telecom subsidiary, and they already, since quite some time, dedicated time to a metric component. We'll see this later on. And yeah, what we created is like polling somewhere, writing metrics on the remote nodes, and have it controller centralizing, shipping this data centralized, showing them centralized. And one little part of this whole picture was an SNMP component to do SNMP in a fast and performant way. And for this, we really tried SNMP libraries from a lot of languages, from Go to Rust and so on. And then by the end, we rewrote SNMP from scratch, a new library that allowed us to do really fancy stuff. Yes. So this was a lot of fun, and the target was to, well, maybe ROCCO, yeah.
Okay. First of all, now I know why Thomas hates me, so it's because of a MIB browser. So silly petty, but it's okay. I will cope with it. Let's talk about the target of the project. This module can be used by everyone, so everyone can gain advantages from this module, but where it really shines is an enterprise scale environment. So we chose the partner from Würth Phoenix customer. Partner is Irideos Red Elite. Actual name is Red Elite now because they're changing the name. Why Irideos is the perfect fit for this module? First, they are an internet service provider, an ESP. So this is the most network-oriented customer you can have. So it's a good place to test this module. Second, it's about the size. This is one of our biggest deployment of NetAI and of course of Icinga because it's only monitoring. As you can see, we have a 3-way cluster with 52 cores per node that is helped by more than 60 satellites and resulting in more than 600 CPU cores for monitoring. We are monitoring actually 350,000 hosts and services, around 46,000 checks per minute. Not so much, too much, don't know. We are doing it. And of them, 40,000 are only SMP. Doing some math, we have around 20 satellites only dedicated to network monitoring. This is a huge number, and it is bound to grow because Red Elite is expanding its business. So we can take a look at the typical day of the NetAI infrastructure. This is a 24-hour span, and we can see the load per core of each server. As you can see, the situation is pretty well balanced because every lines are around 04, 05, 06, so it's almost okay. But still, we're talking about more than 300 CPU fully running. And this is a lot of power. It's not scaling so much, so we have to find other ways, and this is why Thomas is here. So if we have to improve SMP monitoring, we have to understand what we want to have, so the basic issues that are behind the monitoring. The three most important. First of all, monitoring plugin efficiency. This is not strictly related to SMP, but is also related to Icinga in general. When you want to check something, when Icinga needs to check something, what he does? He loads the plugin, the plugins in memory. Then, if it is a script, he has to load the interpreter and parse and compile it. This takes a lot of time, a lot of computational power. Then the plugin is executed. The plugin gets data from the device he needs to monitor. If it is a stateful plugin, he needs to load the state from the disk, from the cache where it is, compare the current state with the old one, then save the new state, output the metrics, the plugin status, and then Icinga can finally unload the plugin. This is done every time a check is run, so it's consuming. And if you know the definition of CPU load in a Linux server, you know this whole process consumes 1 point of load for the time it is required. How much time? Let's see. We're talking about SMP monitoring, so why not going through SMP monitoring, SMP interface monitoring? Some tools to do it. We have Check and WC Health, the Swiss knife for the network monitoring. How much Check and WC Health can we run each second for each core? Around 2.2. Not so much. We have to scale. Sorry. We have to scale. So let's use some more specific. Check if traffic 64. 6.4, 6.5 per second per core. Good, we are making a huge improvement, but this is not enough. For the ones that are using Centrum plugin, the time is similar to the check-if traffic, so they are not that boost to your performance. But they do a well job, okay? They do a good job, so it's fine to use them. The last one, check SNMP. It's a binary, so it's fast. He gets less data, the minimum required, but we can run more than 100 per second for each core. This is what really performance is. So, long story short, complex scripts are helpful, but they are a system killer. So we have to go with something simpler and more efficient, like a binary one, or something that does not need to be compiled every time it's executed. Second point, it's all about precision. Monitoring something is sampling something, so we have to set the right sampling frequency. Otherwise, we can see something that is blur, so it's not reality, and we have to set the right sampling ratio, and we have to cope with the hardware limitation and software limitation. The device is fast enough to answer you, it provides the data, the right data, the software can process this data, a lot of questions. But going back to the sampling window, it's common knowledge that 3-minute or 5-minute sampling is enough. I don't think so. So let's see why. About the transfer speed, let's continue talking about network interfaces. A network device has no concept of speed. It provides us with cumulative counter. So what we have to do, we have to calculate the average speed between 2 points in times. And obviously, if the time between the 2 points is larger, the resolution is lower. So just the core question is, how much data goes through the interface between the 2 points in time? Well, let's look. Just the fast Ethernet interface, the 100 megabit interface, is the slowest one now. If we suppose a 50% load on the interface, so around 5 megabytes per second, after 3 minutes, we moved around 1 gigabyte of data. This is plenty of room to hide several peaks, so it is not enough. We have to go with faster monitoring. Let's have just a simple simulation. So in an ideal world, let's suppose we have to transfer a 20 gigabyte file over a network link with different speeds, so fast Ethernet, 1 gigabit Ethernet, 10 gigabit Ethernet, and then look at it with different sampling window. Sampling every 5 minutes. Good for fast Ethernet. We can see the shape of the transfer, but 1 gigabit Ethernet and 10 gigabit Ethernet are almost equal. This is not good because it is not possible. So 10 gigabyte Ethernet is 10 gigabyte. It's 10 times faster than 1 gigabyte. So this is not enough. We have to go. We have to use a higher ratio. Every 3 minutes. Oh, not so good. We have to go. We have to go further. So with 1 minute, 1 minute is mostly fine for 1 gigabyte interface because we can see the shape of the transfer, the bandwidth occupied in several time slots. It's good, but the 10 gigabit is still one peak, and it is not enough. So we should move to 30 seconds. Is 30 seconds this? Yes. Still one peak, not enough. Going to 50 seconds. Every 50 seconds we can see something. So 50 seconds is the minimum. Is the minimum time window to monitor a 10 gigabyte interface, and we should remember it because otherwise we don't know what are monitoring. The last point is the most controversial one. Counters are registries, so registries are bound to overflow and reset. How often this happens? Network devices provide both 32 and 64-bit register. 32 and 64-bit wide registry, and the plugins have the ability to try to understand and get the correct counters, but this not happen always. And we also have older network devices in our farm that use only 32-bit counter. So it is difficult. We must understand which counter have to use. And if we stick with the 32-bit ones, we can. How often we have an overflow? Every 100 megabit per second, we can have an overflow after 42 seconds. So this means monitoring at every minute or more means loss of data. So make sure you are using 64-bit counter, or are you use a sampling rate that is higher than 1 minute. Otherwise, you are out of the business. How does this impact your real life operations? Okay, let's see some real data. We have a core switch that we sampled every 30 seconds by using telegraph, and we can use Grafana to simulate the downsampling. Traffic at every downsampled at 5 minutes. As you can see a shape, look at it, memorize it, and the peak speed is 24 megabytes per second. Now, if we go down to 3 minutes, the shape is different. Some peaks are appearing, and the peak speed is 40 megabits. Why? Because the resolution increases, so we can see more details. And if we go down to 1 minute, it's more detailed, but the peak speed goes also up. goes up, so this is a problem. And if we go down to 30 seconds, we see the full picture, and it is quite different, and the peak speed is really high. So as you can see, we have to go down under the minute, otherwise we are not seeing anything. And this is what we want to address with the module provided by Thomas.
Yeah, so the solution was easy, just check it faster, you know. If you have thousands of checks, run them every 10 seconds and you're fine. Just the problem is it's very expensive. And while such a plugin is running, it's occupying that amount of memory it needs, and if you have lots of them in parallel, you are very fast blocking more memory than you have, and then you start swapping, and then things get, of course, really bad. So I told you we wrote a remote polling software, and it works like this. You know, you have a central node, some remote node connects, and what happens then is it says, oh, there's some nodes, and he has a look to the database to figure out whether it knows about it, and then it figures out, okay, this one is like, I don't know, running the discovery for a lot of devices, and has already inventoried a lot of devices, and then it just sends the credentials for those devices next to the data to that remote node, and to allow that node to work autonomously and to run or to poll or to run those checks at very high intervals. The whole project has been written in a way that a remote node can work alone even for quite some days without having any contact to the central database. So you need to talk to the remote node just if it has to learn about new credentials, new devices to monitor, and so on. Technically, it is just a sneak peek into the code. It's like right now we wrote it in a way that we can write scenario files. So everything should work out of the box. I want just to define this, for example, a definition for the interface stack, so you can have stacked interfaces on network devices. And this is a point where SNMP can get complicated. It's just one simple example. And with, you have a compound index. So on that SNMP table, you have multiple OIDs used for an index. This is a simple one. If you have a BGP peer table with IP version 6 members, then you have first one number telling you whether it is an IPv4 or IPv6 address. If it is IPv6, it is not a native type. Then the next number is telling you the length of the OID points that make part of this index, 16 for an IPv6 address. Then you have 16 numbers, 16 points for the IPv6 address. Then you have the same thing again for your peer nodes, and this can get quite complicated if you want to implement this. So we abstracted this away and wrote code that allowed us to define it. I have an SNMP table and I have an index. This is the higher or lower stack with a specific OID, and there are other parameters you do not see right now here, where you can also specify the length, or you can tell it whether it is not an explicit, it's an implicit index. So you tell it, well, the next number is going to tell you the length of your part of the index. And this just to abstract away all the code you need to write if you want to implement this complex magic in your own code. So to have something like this, I just have to give it some definition, and it works. Future plans are that you can use the same logic for completely custom checks, and with the MIP browser at hand, we have all the data we need, because in that database we have the definitions, we know about the indexes, we know how long they are, and so on. But right now we are just implementing all the basic stuff to have a lot of things just out of the box. Then next part is I'm going to tell it that I want to have this data in a database table, but this is a remote node without database access. I'm just telling it that I have a table called network interface tag. I want to have a device UID, something I'm not going to pull from the device, and I have the lower and the higher index. In the class itself, I tell it, well, I have a property that's a UUID, and I want to have it in this database column, and this is a device identifier, so this is with every check result enriched with the device identifier. There are more helpers like this, like, I don't know, storing the node where I'm polling and so on. And what's funny here, if you walk one of those index UIDs on one of your switches, you get no result at all, because they are defined in the MIP, but they're not even available for polling. So you poll, for example, the interface tag status, and part of the result OID, after the first points of the OID, there is a number of the higher index, and after the second or after the last point, there is the lower index. So you have to know, I have to take those two numbers and write them to these properties. And this happens in a kind of automatic way. So I tell him well, this property here picks an index value, and please pick this part of the index, and the index definition tells him how this looks like. Another example where we pick metrics, because sometimes I have scenario files where I also want to draw what I poll. And here, for example, I have an interface traffic. You see the default interval for this scenario is 15 seconds. By the way, ROCCO did a very nice explanation showing us how fast interfaces should be polled. But right now we are talking, you can buy a switch with 244 ports, each of them running at 800 gigabit per second, and 1.6 terabits is just around the corner per interface. Those switches are running on all interfaces with line speed encryption, so they can run all 200 and something interfaces, like this. Every one of them right now with 800 gigabits, and all of them encrypted at line speed. This means all of them in parallel can ship encrypted data with the performance that is specified by the vendor per interface. And so 1.6, if this is not enough for you, 1.6 terabit per interface is being standardized right now. The standardized, the physical parts, just there's some other details that still have to be defined, and then you can buy them also if this is not enough for you. So we will go faster in future. What's new here is I did tell it as well. The scenario file here is also a measurement. It's called interface IF traffic, and here I have in this file just 3 OIDs. So there are more OIDs in other files. For example, we are pouring the errors from the interface in a slower rate, because it's just important that they are there. We do not need them with that precision. Here I've just the octets, or the bytes in and out on the interface, and well, I tell him this is a counter. Pick, yeah, that's the name. Write it to this variable, and that's it. And this will then be shipped to some metric writer with those details for every result. Also here currently it's just for ourselves, for the scenarios we ship out of the box, and the idea is that in future you can just click some OIDs and say, well, I want to have it in a database, I want to pull it, and so on. And I want to draw them. Currently the poller itself is structured in a way that each of these scenarios has its very own scheduling instance out of the box. You add a scenario, it's running, and it's going to be scheduled for all the nodes that need to to be built that way. Currently, it works in a way that if one node has few devices, then it just creates 20 slots per interval and distributes the nodes in a reproducible way, being hashed over them. If you have more than 1,000 devices, then it creates 200 slots in the time period. So, and it also adds some time at the end for as a grace period for the results. So let's say if you have 10,000 devices for the interface check every 15 seconds, then it just creates 200 slots, places the devices in all of them, and runs those 200 slots in 10 seconds, not 15 seconds. So because it's also reserves some time to get the results. It's no problem if it takes longer. It's really written in a way that if a device is slow, then it takes longer. And all components, even the SNMP walk, for example, is written in a way that we fully control it. So I can say, well, pick this part of the walk from that node, and there are a couple of thousand other nodes in the meantime, and then finally this part arrives, and he picks the next part from that node, and so on. So we have full control over this, and can work with fast and slow devices in parallel. Yeah, please. So the question was the difference between just getting traps and running those active checks. We implemented a trap receiver just to figure out whether it works, and I really had trouble to ship that many traps it could handle. So it was easier to write a trap receiver than writing something that ships that many traps. So it worked with our code, but I didn't trust it, so I wanted to use other tools. But sending traps with SNMP on command line is extremely expensive, even if it is written in C. So that's terrible if we want to ship lots of them. But we can get traps. It's just for right now it is a lower priority. The nice thing if we receive a trap in future is we have right around the corner. So we have that MIP database, and we know all the details about the trap. For example, there are some vendors that ship traps where the OID changes with every trap. Like, I don't know, the Oracle Enterprise Manager ships. No, that one doesn't. That one is just complicated with a lot of OIDs. But that's some devices send you traps with a new OID every time. Because it's just the data type in the trap is kind of a table, so you get a new entry for this table with every trap, and defining something with some mapping on disk is pretty hard for something like this. And this is where a lot of tools struggle. And we have the luxury that we have a database where we know that this is a table. We know this data part, this value is a table entry, so we are able to handle those things just out of the box. But this is something with lower priority. We will also work on this right now. We're just talking about active polling. And also there is, currently I have one artificial limit in there, but just to not let it go wild, because I have been granted access to the Irideos network and working with their real live devices. So in theory, you can write a lot of codes, but only when running it live on real devices, you understand whether it is working or what is going wrong or what you could expect. And so there are some artificial limits. For example, in one slot at once, I sent no more than 10,000 pending. Oh no, in total, it doesn't allow more than 10,000 pending requests for all devices in parallel, but just because I defined it is, so we can go way higher. And this is only on one node. Or on one instance, you can run multiple instances per node. SNMP version 3 is pretty cool because I don't know if anyone already looks a little bit deeper in SNMP version 3. If you just don't even want to encrypt it, just authenticate in a secure way. It picks your secret and writes secret after secret after secret after secret unless you reach 1 megabyte. and then you have to cut it exactly at 1 megabyte. Then you pick a hash of this one, SHA1 or SHA, whatever. You can also use newer algorithms. Then you pick this checksum, use a checksum, use the engine ID, or you do not have the engine ID, so you have to ask the device for the engine ID, pick the engine ID, write the engine ID there, once again the former hash, then once again a hash of all of this, and then this is the string you can use for authentication. And for encryption, it's even more complicated because there is a time-based component. So you, at least every 150 seconds, you have to pick the device uptime or the engine uptime to do more stuff there. This is expensive, and the plugin has to do this at every run. We just calculate this once per node and refresh it if necessary. We have one of these scenarios is a keep alive check that runs every 10 seconds for every device and just gets system name, the engine ID, and engine uptime, and so on. And if a device doesn't respond to 3 times, it is considered down, and all the other scenarios stop for that device. And every time you get a change in these data, it automatically refreshes the authentication part if you are running SNMP version 3. So this is just there waiting in memory, and this is really fast. Some of you might wonder why SNMP. Today we have it's pretty old, you know. It has been invented 30 years ago. It's completely outdated, it's complicated, it's slow, it's insecure, and so on. And today we have REST APIs, we have gRPC, open telemetry, and so on. And this is not true. So it isn't 30 years old, it's 35 years. You have to be precise. And it's not outdated. You know, the World Wide Web, what Tim Berners-Lee did was the basics have been developed in 1989. The web is still working. Yeah. And as of today, the most devices still support it, and this is the protocol with this one you can get most of them. Of course, there are more fancy protocols on new devices, but they have their very own problems. And SNMP isn't complicated if you understand how it works, and we want to make this easier for you. I have to speed up a little bit, I'm sorry. It isn't slow, it really isn't slow, and it's also not insecure. With, you can use SNMP version 3 with encryption and hashing since 1999. This is when it has been standardized. I could have used it before. Still, a lot of people are running version 2 because either your monitoring software doesn't support it or it is just too expensive for performance-wise. Today we have modern algorithms, we have replay attack protections and so on, so it is pretty secure. You can use REST or gRPC on modern devices, but please talk to people who are doing this in real life. As you run into very scary bugs, and you do not want your switch to crash. So today, most switches do not crash totally. They are like Linux systems, and you have a process running there doing SNMP, so just that process crashes. But just then picking the core dump and writing it really breaks your switch for a short moment, so you feel it even if the switch goes on and you have just chips doing the switching. It has a performance impact. And there are scary bugs, and you have to deal like with problems like it's complicated to define and to configure, so you can easily end up with way too many metrics, and influx is giving you problems because you are hitting hard limits there or soft limits and so on. So it's not all that easy. And for us, here it is all about the data. I picked a blog post on the Cisco website, just as an example from August. And they were, Cisco drives full stack observability with telemetry, and this sounds very, very good. And my favorite sentence was, to assess this telemetry, you need AI and so on, And this sounds great. But to me, this reads like we're collecting a bazillion of metrics, and we have no idea, no clue what to do with them. This is when you need AI, and we have other ideas. We want to have just the data we understand, and we work with exactly that data. We do not try to do everything at once. Begin just with the important parts, and want to make it easy to add new features. So this is one of the core ideas here. We want to own the data, so we want to model it in an opinionated, meaningful way, and this is where the inventory part kicks in. Just very fast, running out of time. This is central. it's a relational database, and here we have a lot of information that doesn't change. It is like it is, site information, racks, offices, plans, vendor information, information about the models running in your switch and so on, and not outdated ones. The database is modeled following SMI from the MIP SNMP world, but also following what we are seeing today with Young and Netcon, so the modern world. Their discovery rules, their credentials, and so on. I can install software, for example, for a Linux system if I want to pull them with SNMP and so on. So lots of data there. Network ranges, CDP, LDP neighbors, and so on. So the schema gives a lot of information, and to invent something new, I just have to create a scenario file, create a table, and it's there right now. Some screenshot how it looks like. This is just a prototype, so the hard work is right now going on under the hood for the polling and that part. This is where we started. Like, you have some devices. You initially I had just pictures, so I had a model. Okay, this is this hardware model. I have a picture. Let's show the picture. We have metrics. We'll see it immediately. If I do not know which model it is, it just invents something and shows you the hardware ports in some specific way. The rendering here, we worry by ourselves. So when showing an interface, even with lots of them on a single page, I control all of this. So I can show, depending on the speed, different lights here. If it is not connected, I show it like this, where the cable is missing. Here, the interface is administratively down, so you see it in a different color, and so on. I can control how the pins are rendered, and yeah. Depending on the current traffic, the color of the interface is changing. We are polling every 15 seconds remotely and writing metrics remotely. We do not want to have it at this precision in a central database. This would kill us. So in these scenario files, I can define aggregation rules, and I want to have those metrics aggregated just every 5 or 10 or 15 minutes and have them in the database. This allows me to know about hundreds of thousands of interfaces and have the current speeds aggregated over the last 15 minutes for all of them. So I can tell him, give me all interfaces in that specific private VLAN sorted by current traffic in just one data center, for example. This is what we want to have in the database. Then we went on and combined both worlds, and from the device I get the information which modules are installed. From the database I get the information how that device is structured, so I know that this region here is the power supply bay 0. I have to go on faster, sorry. If I have, this is currently work in progress, but if I have SSBs and have fiber there, with the sensor data at the center here, I am showing the quality of the signal, so the decibel, the loss you have, and outside here you can see the current performance, the current traffic, depending on what the interface is able to ship. I have the data right there in the database, so this is what just a snippet of what we get. This is part of the chassis we have seen before. We see a chassis, a subslot, a transceiver there, and the transceiver is an SFP with 10 gigabits, and these are the sensor data we have, and this is the loss we have on performance-wise on the fiber. With this data, we are rendering what you are seeing. And, I'm sorry, I have to speed up. Metrics, many thanks to Irideos. I'm sorry. They sponsored and dedicated a lot of time to writing a metric component for Icinga. We used that part and rewrote it in a way that it can run on that remote data node as a feature there. So this is, the data nodes are modular, I can run features. So we collect remotely, we write data remotely. And this was one of the initial screenshots. This is a real screenshot, not faked. Behind this is running ROD. A lot of handling around it and running very fast, but in reality it's ROD files. And on their setup, we are running it in production since a year right now with an early prototype and collecting data from, I don't know, 1.5 million data sources, and it makes absolutely no stress on that node. It's really, it's nice, and it looks nice. ROD hasn't to be ugly, and because it is so fast, this is just one simple image, but you can see here, this is being run remotely. So the remote node, I give it the instruction, the remote node gives me the image, and in 1.9 milliseconds, not seconds, 1.9 milliseconds, I get an image like this. Of course, it's like 10 milliseconds for a normal image, but it's still way faster than everything else we have. And it's so fast that we can use it integrated in a lot of UI components as a feature for everything. Here we see 10 data sources per image, 8 of them together, and I get all of them in 0.0 something seconds. It's extremely fast. This is just the templating for this, looks good, and so on. So you might ask where can I get it? We're still working on it. So this is so this year we wanted to have it at a stage to have it running live around the clock at Irideos at the customer. It already works very well, and just currently I started when I work on it, and I stop it in the evening just to be sure that it doesn't go wild. The MIP browser is already on GitHub, at least the first release. This, of course, without the polling hook, because this part is still not online. And this will everything will be open source, and once we settled the basics, we'll have a sooner release. And next year is going to be a very nice round product. So our idea is to have it really rock solid like vSphere-DB. And yeah, if you want something like this, want to be an early adopter, we are looking for people that prefer to let me test it in their production. I'm interested in setups with strange devices, vendors that are not so usual, but you have lots of them, or large deployments with SNMP version 3, because this customer production has only version 2, so this we test as version 3, but we are not running it at scale right now. Or for example, if you have a network with lots of visualization, MPLS, private VLANs, and so on, and so if you're interested and want to be on the ship early on, just let us know, please. This would really help the project, because it's a completely open source project. So, yeah, this helps. Thank you very much. Sorry for going a little bit over the time.